In the previous episode, we saw how forensic physics transforms evidence into proof. We learned that measurement, uncertainty, and physical laws form the foundation of courtroom science. In this episode, we move from static evidence to dynamic events. We examine crimes where motion plays the central role. Violent crimes are rarely stationary. They involve movement, impact, and rapid energy transfer. Blood travels through the air. Bullets move at high speeds. Bodies fall, recoil occurs, and objects collide. Each of these motions follows physical laws. Forensic physics treats violent crime scenes as records of motion. What appears chaotic often has an underlying geometric order. The key question is simple. Can motion reveal where people stood and how events unfolded? To answer this, we begin with why motion matters in forensic investigations. At a crime scene, the final positions of objects are observed. But crimes happen over time, not instantaneously. Motion connects the beginning of an event to its end. It links cause and effect. When a force acts, motion follows. When motion stops, traces remain. These traces encode information about direction, speed, and interaction. Physics provides the tools to decode them. Courts rely on motion analysis because it constrains possibilities. It helps rule out physically impossible claims. If an object could not have moved in a certain way, the explanation fails. This makes motion analysis powerful in legal contexts. We first examine bloodstain patterns. Despite their appearance, bloodstains obey simple physical principles. Bloodstain pattern analysis is often misunderstood. It is not guesswork or intuition. It is based on geometry, gravity, and motion. Blood droplets behave like small projectiles. Once a droplet leaves a surface or body, gravity acts on it. Its path through the air is governed by projectile motion. The shape of a bloodstain depends on how the droplet strikes a surface. This is where geometry becomes important. A drop falling vertically produces a circular stain. A drop striking at an angle produces an elongated shape. The more elongated the stain, the smaller the angle of impact. This relationship can be quantified. By measuring the length and width of a stain, investigators estimate the impact angle. Simple trigonometry is used. These calculations do not reveal emotions or intent. They reveal direction and orientation. Multiple stains can be analyzed together. Their directions can be traced backward. This process helps identify an area of origin. It suggests where the blood-producing event occurred. Importantly, this area is not a single point. It is a region with uncertainty. Environmental factors affect bloodstains. Surface texture, absorbency, and airflow matter. Therefore, conclusions are always probabilistic. Physics constrains, but does not dictate, outcomes. Bloodstain analysis can suggest positions. It cannot identify who caused the injury. That distinction is critical in court. Physics informs, but does not accuse. We now turn to bullets and ballistic motion. Bullets are extreme examples of moving objects. Once fired, a bullet becomes a projectile. It is acted upon primarily by gravity and air resistance. In many reconstructions, air resistance is neglected. This simplifies analysis over short distances. Under these assumptions, bullets follow curved paths. They do not travel in perfectly straight lines. Over short indoor distances, curvature is minimal. Over longer distances, bullet drop becomes significant. Forensic reconstructions often assume straight line motion initially. This assumption must be justified. Trajectory rods and laser alignment tools are commonly used. They help visualize possible paths. These tools do not recreate the shot. They represent geometrically consistent trajectories. By extending trajectories backward, investigators infer shooter position. Again, results are expressed as regions, not points. Bullet impacts also reveal energy transfer. Damage depends strongly on speed. Kinetic energy increases with the square of velocity. Small increases in speed produce large increases in damage. This is why velocity matters more than mass in ballistics. Physics explains this clearly. However, penetration alone does not determine distance. Many variables influence bullet behavior. Material properties, angle of impact, and bullet design all matter. Oversimplification leads to error. Forensic physics therefore treats ballistic evidence cautiously. Claims must be physically justified. Both bloodstains and bullets illustrate the same principle. Motion leaves measurable traces. These traces are not stories. They are physical consequences. Physics allows investigators to ask disciplined questions. What direction did motion occur? What range of speeds is consistent with the evidence? What positions are physically possible? At this stage, we have examined motion descriptively. Next, we connect motion to energy and impact. That is where deeper reconstruction becomes possible. Motion alone does not explain the full story. To understand damage and injury, forensic physics must consider energy. Whenever an object moves, it carries kinetic energy. This energy is transferred when motion stops. In violent crimes, energy transfer is central. It determines the severity of impact and damage. Kinetic energy depends on mass and velocity. But velocity plays a dominant role. Because kinetic energy scales with the square of velocity, a small increase in speed produces a large increase in energy. This is why fast-moving objects cause disproportionate damage. Physics makes this relationship explicit. When a bullet strikes a surface, its energy is dissipated. Some energy causes deformation. Some energy causes fracture. Some energy may be converted into heat or sound. The exact distribution depends on material properties. Angle of impact also matters. A shallow angle produces a different damage pattern than a direct hit. This information can be used to infer motion direction. Similarly, when blood strikes a surface, its kinetic energy affects stain size and shape. Higher energy impacts tend to produce smaller, more dispersed droplets. Lower energy impacts produce larger stains. However, energy estimates from stains are approximate. They are influenced by many external factors. Forensic physics therefore avoids single variable conclusions. Multiple indicators are always considered together. Damage patterns on objects and bodies also reflect energy transfer. Deformation tells a physical story. Bent metal indicates applied force. Cracked glass reveals stress distribution. However, damage does not uniquely determine cause. Different motions can produce similar outcomes. This is where uncertainty reappears. Physics acknowledges that multiple reconstructions may fit the same evidence. This reality is often misunderstood by the public. Popular media exaggerates forensic certainty. Television often portrays instant, precise answers. Real forensic physics is slower and more cautious. Measurements have error bars. Reconstructions have ranges. Environmental factors introduce variability. Surface roughness, airflow, and obstacles matter. Ignoring these factors leads to overconfidence. Overconfidence undermines scientific credibility. Forensic physicists must therefore state assumptions clearly. Every calculation depends on conditions. If assumptions change, conclusions may change. Courts must be informed of this dependency. This honesty is not weakness. It is the strength of scientific testimony. In court, motion analysis is rarely presented mathematically. Equations are seldom shown. Instead, diagrams and reconstructions are used. Visual clarity matters more than formalism. Experts explain concepts in accessible language. They focus on physical consistency. They do not argue guilt or innocence. They explain what physics allows and forbids. Judges and juries evaluate this information alongside other evidence. Physics contributes one layer of understanding. Because physics is impartial, it protects both prosecution and defense. It can support a claim. It can also refute it. This neutrality is why courts value physical science. It does not favor outcomes. However, misuse of forensic motion analysis is possible. Selective interpretation can distort conclusions. That is why education matters. Understanding limits is as important as understanding methods. This series aims to build that understanding. It does not promise certainty where none exists. Instead, it emphasizes disciplined reasoning. Physics constrains reality. Motion must obey laws. Energy must be conserved. These principles act as filters. They separate plausible explanations from impossible ones. Bloodstains and bullets are not mysteries. They are physical consequences. When interpreted carefully, they reveal consistent patterns. Forensic physics follows those patterns. It does not follow narratives. This episode has shown how motion and energy shape violent crime evidence. In the next episode, we shift focus from motion to time. Estimating time of death introduces thermodynamics. Heat transfer becomes the key. This series is presented by the Physical Sciences Consultorium. PSC is dedicated to explaining science with rigor and societal relevance. If you find this approach useful, please like this video and share it with students and educators. Subscribing to the channel helps sustain future episodes. It allows PSC to continue producing serious educational content.